correctly between the two. So
this is Andrew.
yeah, so maybe Andrew would be good to do the field question and not you, for example. Okay? So can you calculate the answer here, and then I'll open up the market scheme to check that you got the right answer. So I just want part 1 and part 2 first. Just part 1 and part 2.
No, of course. You guys need a question.
Yeah, just relax yourself. Dude, why are you checking your notes? You're the chosen one. You're the only one who knew it. You're the Neo. Ah, come on. That movie. Well, I guess it is kind of old for you. Matrix, Neo.
Nope. We watch Avengers.
Losers.
Is it not actually? Actually, it's sci-fi movie. Yeah.
Stop talking, please. You're making me sad.
Was it like M90?
I'm just ignoring you now. Can you do this, Sean? Part 1 and part 2?
Yeah. Too small.
Too small? Goodness sake. What's the formula for the flux?
Can you use it?
What's the formula for the flux? BA. No! BA.
NBA is the second.
Yes.
No VS?
What's VS?
Volkswagen.
No, that's not the flux.
Did you say that?
No, I said that's the unit.
What is the A?
Whatever. Newton.
Yeah. But that's not a formula. You don't know the voltage here anyways.
If you knew it.
And you knew the time. So the problem with that formula, KJ, is you don't know anything in it. Huh? What's the problem here? Guys, it's just, come on, it's 1 mark. It's BA. You take the B and you multiply it by the A. No, I only asked you to do part 1 and 2. Okay, you have part 1 done. What's the answer for part 1?
1.76.
1.76 what?
No.
Webers. Let me check the answer.
1.77.
OMG.
Times 10 to the power negative 7.
0.250 times 10 to the power of minus 3 times pi or squared. What? Who said? Yeah. It's not 1 point something something. It's tiny. It's this.
Yeah, I told you.
It's 177 nanowebers. Now, I wonder if there's a typing mistake in this question. I wonder if they meant to say 250 and not 0.250 millitesla. Because 0.250 millitesla is nothing. It's not even 1 millitesla. So I'll check the answer to see if they screwed it up. What number is this now? 4. No, they didn't. It really is that small. 1.77 times 10 to the minus 7 Webers. Here, the bottom line. No, because it's not an energy, so we can't use electron volts. Okay, part 2. What's the flux linkage? Yeah, just multiply by 55, isn't it? Huh? Oh, it's if you want to be super technical with the unit, because it was flux multiplied by number of turns. So if you call number of turns a unit, but that seems a bit over the top for me. Yeah, that's it. Just literally multiply the answer by 55 and you get this.
So hot.
Yeah, now, the next one now is a bit more interesting. What is the magnetic, what was the voltage if the time is 1.5 milliseconds? So in Faraday's law, the N you know, and the flux you know. So please, listen, be careful. Either use this answer as the flux, or this one multiplied by N. But don't use this one and multiply it by 55 again. You only need to do that once. So if I use this one, at the beginning we have this much, and then if we remove the magnet, how much do we have? Zero. So the difference is only this amount. So take your answer from part 2 and just divide it by this time. So whatever answer you got in part 2, divide it by 1.5 milliseconds and tell me what you got. Sorry Monica, what was the answer for part 2? Well, this is, okay, divided by how many milliseconds? Okay, so that's 0.0015. So the voltage is 6.5 millivolts. Let me check the answer. 6.5 millivolts.
Oh, that is 4 seconds, right?
Huh?
4 seconds.
No, just good old volts. I don't think there's any volt seconds in this one. Oh, wait, actually no, Webers. Webers can be volt seconds, can't they? Yeah. No, this last one, oh. You could, oh yeah, Webers per second's a volt. So, yeah, same thing as saying Webers a volt second. Okay. So that's kind of a lot of marks. That's 6 marks. 6 marks, not so bad. If you don't screw it up. Okay.
So hot.
Okay, so you have 2 particles and they have the same kinetic energy, 0.18 mega electron volts. Both particles enter a magnetic field of flux density 0.22 Tesla. Why would both particles move in a circular path? Well, using our, which rule is this now? Left-hand rule. And you can see here's the picture here. F, B, I. So the B is into the page. The I, are these positive or negative charges?
Positive. Alpha.
We haven't studied atoms yet, so you actually don't know, but I'll tell you now, the alpha one is a positive particle and the beta one's a negative.
Oh.
So, for the alpha, the current is going to the right, so which way is the force going? Up, yeah, and then for the beta, the force will be going down. So what will happen is, the alpha will come in and move in a circle upwards, and the beta will come in and move in a circle downwards. Explain why both particles move in a circular path. It's because of the left-hand rule, and that the force is perpendicular to its motion, which is kind of what you need for circular motion, because if you think about a motion in a circle, if this particle is moving this way, the force acting on it is perpendicular to its velocity. So FBI, the current is a bit like its direction, because remember, whatever way the alpha moves, that's the way the current is moving. And because that is perpendicular to the force, that's what will make it move in a circle. So in other words, because the left-hand rule and that force is perpendicular to current, that is what makes it move in a circle. So that answers the first part. In the second part, they want their energy in joules and their mass in kilograms, and then from using that, calculate the speed of the particles. Now, let's have a look. Do we have enough information to do that? We do, because we know the kinetic energy, and the kinetic energy is a half mv squared. So if you knew the mass, which you don't know yet because we haven't studied it, you could know the V. And then from knowing the V, you could know the F, because what's the F here? What's the formula for force in the magnetic field? No? In the magnetic field. We'll get to that one in a moment. Yeah, QVB. QVB. We know the Q, we know the charge. We know the V, they just asked us for it. We know the B, they give it to us. And as you said, Monica, that would be the same as mv squared over r. And we already know the V because they asked us that as well. And we know the M. So everything is known in that formula except for the or, which is what they want. And then the last part is to sketch it. So again, you're looking at it and you're thinking, yeah, that's alright, maybe I'll do this in the exam. But let's have a look at another year. No? That's not what you're thinking?
Teacher, how we know which hand we use?
Just remember,
Left hand rule.
use the left hand rule when you need to and the right hand rule when you need to. It takes me a moment to remember which way it is as well. But the order I remember is right hand grip, left hand, Fleming's left hand, Fleming's right hand. So it's right hand grip around a wire, left hand for motor, right hand for generator. Let's have a look here. Yeah. Okay, let's see what the fields are like this one. No. Electron volts. Yeah, okay, here's a... no, we can't do that one yet. That's the mechanics. Electricity. Lee, you're distracting me.
You're a very
We've got this fella again. This guy's back. Okay, I feel like I'll go to a different year because these are kind of similar. So let's look at the next year. 2007. When Jerry was born. Right. What? Nothing.
No, I'm for
Oh, close. Close to 2007.
Yeah.
You were 1999. What difference is it?
Oh, you're so last century. Yeah.
How old are you? 2006.
2006. Shit. 7.
Okay.
There's a transformer question. That's electricity. What the heck is that? That is electricity again. That's a projectile. An atom. And atoms again. Ah, here we go. Huh? And maybe the fields question isn't great here. Yeah? What's wrong with that as a username? Jealous? What's yours? Lee Win 2000 and... No, sorry, Lee Win 1999, is it?
Kinda, really.
Yeah.
Oh, sorry, Win Lee 1999, is it?
Win
Or Lee So Much Win 1999.
Stop. Stop guessing.
That's amazing.
I like that one now, actually, yeah.
Winner 99.
Stop guessing.
Yeah, he doesn't want us to friend him on Steam. It's like, hey Lee, want to join my campaign? I'm storming some castles now. Okay, I'll be good. I'll be good! Let's see. Atoms. Ah! Oh, smoke one again! Again, that's 2 years in a row they did that smoke question.
Let's make it 3. Oh.
Ah, now we're talking.
Can
Okay.
you say rapper for the
Oh,
question?
smoke.
Huh?
Can you say rapper? Just say rapper.
Weather?
The question is rapper.
Ah! No. You can't. I don't want to do this part. I'm so sick of this smoke question. I've seen it so many times, and we did it in class. It's a pain. Let's just look at the A and the B part here. Okay, so let's do this one. Right. In Faraday's law, what does that symbol represent? No, that's the unit. It represents the magnetic flux, which is measured in Webers. Okay. What is the importance of the minus in the formula? Yeah, in fact, that has a name. That's a law as well. What's that law called? Lenz's law, that says the current induced will oppose the change in the magnetic field. Okay, B part 1, a circular coil of metal wire of diameter 5.5 centimeters has 280 turns, and its resistance is that. The coil is placed with its axis parallel to magnetic field, with flux density that. If the coil is removed quickly, what is the EMF? Okay, so you've got a metal coil, and you've got a coil of metal, like copper or something, and there's a magnet inside of it, and then you pull the magnet out, and you'll get, for a moment, a voltage in this copper wire. And for tree marks, they want to know what is the voltage, and of course they even help you by having this as the first part. Now there isn't an N in this formula, because in this one they have the N already calculated inside of this, but you can put the N on the outside because it's a constant. In fact, you can put the A on the outside as well because it's also a constant. Can you try B part 1? And you have to think to yourself, is there a reason that they gave me the resistance? Or are they trying to trick me into giving me information I don't need?
Trick you.
No, it's not a trick. Oh.
Calculate and see if you need it. B part 1, please, Sean.
Okay. I'll have to write that down.
Now, I'll tell you, you're right. You don't need the resistance, but you actually, I think, might need it for part 2. So it's not relevant for part 1. Let me close Steam down.
Oh, look, you have steam!
Oh my goodness, that's like the 3rd time. Everybody has Steam. What? Well, of course play games. What else do you do on Steam?
Okay.
Ah, yeah.
Oh.
Well, you can see the game my friend made.
Your friend made?
Trinity friend. Oh goodness, it's been a while since I played this.
How hard to make this game?
How this like? Oh.
What are we playing?
Not hit the wall.
What? Oh.
And the little arrow. Ah!
Oh, nice.
Yeah, see?
Oh, the arrow.
See, it's hard. It's like the game you were playing, Lee.
Huh? What's this?
Oh, it's fun. You will warm me after playing this game.
This level, the most I got is 30 seconds.
You die from this.
Huh?
This is not easy at all.
And this the difficulty is difficult. Hardest one.
Yeah, the first level is 69 seconds, then 64, and then 31. Yeah, lame. Alright, away from that. Okay.
Oh.
My friend made that game. It's on Steam.
How long?
Huh? Oh, that game wasn't too bad for him to make. Maybe he made that in like 2 or 3 months. Not too bad. The previous game that's on Steam took him about a year to make.
How to make games?
Programming. Maybe you know his other game?
You mean?
VVV?
No,
Okay. Right, do we get an answer here for this one?
Yeah. 0.0.
That's small. That's small. Let me calculate it here. Right, so firstly, what's the time? 0.0015. 280 times BA, right? B and the A. And what's the R, please? 0.055. Oh, that's only the, yeah, so 37.7 volts? No? Monica? Yeah?
Quite high,
Oh, the diameter is 5.5. It says it there.
shouldn't be
I did. Yeah. Okay, is this okay? Now, part 2. The same coil in B part 1, so the same metal coil, is now connected to a voltage of 110 volts. But that's alternating every 50 times a second. Explain without calculation why the current will be less than the value calculated from Ohm's law. Now, we didn't actually calculate the current. I think they maybe meant to say here, calculate the current, not the voltage, possibly. Because why bother giving me the resistance, only to tell me later not to calculate it. So, the question is then, why does the current reduce? Well, I'm going to ignore there without calculation. I want to see what the current is in this part. Okay, so we have V equals I or, so I is V over or, so V over or, and the or is 0.64. So in the beginning, it's 58.9 amps. So you have your coil, and the magnet comes out, and because of that it causes a 58.9 amps, and what did we say the voltage was? 37.7. Now what they do now is they say they replace this coil with a voltage of 110 volts. And they want to know, why does the current decrease? No, I thought you were going to say it. No. You have this formula VIOR. Okay? So the I here is V over OR, and the I here is V over OR. Now, you know that this V is bigger. Oh, sorry, it's smaller. No, sorry, it's bigger. Sorry, it's bigger. And you know that this V here is smaller. And they're saying, explain why the current will be less. Well, you don't even have to calculate it. If the V is smaller, the current is smaller. Only if the OR stays the same. And that's exactly what Ohm's law is. It says by using Ohm's law, if the material is ohmic, do you remember this word? Ohmic means that it's a straight line, which means the slope is constant, which means the resistance is constant, which means the resistance does not change even as you're changing the V and the I. So if the V has increased, then the I has to increase if we consider the OR has to stay the same. So it seems like a lot, 3 marks. So the answer would be, yeah, using, yeah, but I'm not going to do any calculations, I'm just going to use the formula. Using I equals V over OR, if the material is ohmic, then OR will be constant, and so an increase or decrease in V will see a proportional increase or decrease in I. The question is, the same coil is now connected to a voltage of 110 volts. Oh yeah, because the voltage has, why would the current be? Oh, I misread. Oh, it should increase then. The voltage has... no, don't write this down. No, well, what I wrote down is still true. No, if you want to write down, it's still true. But it's only true for DC. So how does it be in AC change it? So in the question they're saying, explain why the current will be less. Yeah, explain why the current will be less than the value calculated from Ohm's law. In other words, why is it wrong to use the Ohm's law here? Yes, there's another reason too. Yeah. Anyways, sorry about that. I misread. I forgot that it was an AC current. I thought it was a DC current. The picture changes if it's an AC. For AC, your formula VIR, this is only for a DC. You have to, it's a little bit different when it's an AC. And you know that other formula, OR equals rho L over A. Again, that's for a DC, not for an AC. So as Monica is saying, the resistance has changed. Now, how has it changed? Like, why has it changed? Why does being AC change it? Well, we actually haven't talked about this in class, but the reason is this. In this formula here, this is only for DC. We haven't done the one for AC. By doing the one for the AC, there's a small change in the formula. You have to put a little constant here. Now, I can't remember the value of the constant. It's something like 0.7. In other words, it has the effect of reducing the A, which has the effect of, if you make the A smaller, you make the OR bigger. Okay? And if you have the formula I equals V over OR, and if you make the OR bigger, then what happens to the I? It becomes smaller. Now, I don't think they will ask you this because it requires you to use something which is not on the course. We never actually said this in class, but you might be surprised to discover that if you have a wire and you pass an AC through it, or you pass a DC through it, you actually get two different resistance. Using the formula we did in class, resistance is rho L over A, or using this formula which we haven't done in class, which is something like this. So you can see rather interestingly that if you use an AC current you get less resistance. You get more resistance. Now, just think about this for a moment. If you get more resistance by using an AC current, why do power plants use AC? Like you might be saying, oh, so they would save energy if they use DC, because there'd be less resistance in the wires and there'd be less heat. So why on earth would they use AC and not DC? No, you don't want heat on your power cables. So here's your power plant. KJ. Here's your power plant. It sends the electricity to the home, and it uses an AC current to send it. Now, of course, it's wasting energy because there's a little bit of heat coming off these wires, and it's because of the resistance in the wire, which is rho L over something like 0.7 A. Now, if they can use DC...
Is it related to transformation?
Yeah, it is. It is related to this, yeah.
Efficiency.
Where?
Yeah, can change the...
Not quite that. I'll tell you why. In the power plant, remember the AC generator, it naturally makes AC through the process of turning. If they wanted to send this as DC, they would first have to change the AC at the power plant to DC. The energy needed to make this transformation from AC to DC would be more than the energy you would save by using DC instead of AC. So although DC would be better to use, the cost to actually make it to begin with would be more than what you would save from the heat. So it's actually just in total better just to use AC, even though you would get less resistance if you used DC. There's some people who think perhaps in the future, as technology improves, all power plants will use DC, and it'll save energy getting to people's home. How much energy do you think is wasted from the moment the energy is, the electrical energy is made to the time it gets to your home? What do you think the efficiency is?
Power...
70%, okay?
70%.
You're saying 70?
70.
You're saying 10%. So you're saying 90% is lost?
70%.
You're saying 70?
Lost.
Well, maybe in China. What about in Ireland? In Ireland, it's 50%. Yeah.
Lost DC. AC.
In Ireland, when we make, for every 2 joules of electrical energy that's made here, only 1 joule gets to the home.
Yeah.
Because it's lost by heat, lost by many things along the way. It's a lot, isn't it? So it's like you pay for your electricity twice.
How much?
In Ireland, I think it's about 15 cents per 3.6 megajoules. I think.
Why
Yeah.
do we use DC?
Huh?
Why do we make it?
Because I use heat power.
Like I said, because the energy required to convert it will be more than what you would save through the heat.
So for making DC and transfer it into the whole so expensive.
Yeah? Yeah. Say again?
DC.
Oh yeah, but the problem is, remember that we did the generator? Generator makes AC naturally. You would have to convert it into DC. You can't make DC from the beginning. It always is made first as AC. You would have to convert it into DC. This conversion requires more energy, and the energy requires is more than what you would save through the heat energy.
How much?
It's not too bad. You can use capacitors to convert it. So if you have if we think about our AC graph like this, what you can do is you can have capacitors charging up, so that when it gets back to here, when the voltage is quite low, the capacitors will discharge to make it higher, and then when the voltage is quite high, the capacitors charge up, so then the voltage is reduced. So you can change this graph into something that looks maybe more like a bit maybe flatter, but then you don't want to change in the direction. So this is the hard part. How do you change the direction? So one really stupid way of doing it is you have something called a diode. Every time the current passes through this way, you let it in. but when it passes through backwards, you don't. Now, of course, you realise that's stupid because it means you lose straight away half your current. The diode heats up. So now you have this graph. But if you use capacitors, then when it charges up here, it will discharge here. So the graph could look like this. Something like... and then you could put in a couple of more capacitors and you can smooth it out. But already this is only 50% efficient because you have to throw away this. So what could you do? Well, maybe you could take the current and flip it around. But how do you flip a current around, you know? Maybe, no, you're right. Some kind of switching mechanism perhaps. So you have your current here and you have two connections here and you have a switch. So when the current is going this way, the switch can be in the up position, and then this can pass around. And then when the current is going backwards, it can this can close, and I don't know. You'd have to have it if it's going this way. It's going to be hard to draw. This is when it's going forward, and we're happy. Then when it's going backwards, we'd have to have the wires kind of connected in such a way to turn them around. Anyways, you're right, you could have some kind of switch. How quickly would this switch have to move? But if the AC is 50 Hertz, then the switch also would have to be 50 Hertz. And what would happen if the switch was no longer in time with the current? You know, when the current was going down, the switch was in the up position. Then everything gets reversed. You know. So anyways, the point is, it's hard to change AC into DC. Now you actually all have a way to do that at home. Your charger for your phone uses DC, but this is AC. So actually your phone charger converts from AC to DC. But this process is not perfect, and that's why the phone charger can sometimes get warm. Because it depends on how it converts it. If it uses a diode just to throw away half the current, then it will warm up. I don't think it's using a switch because you would hear it. It might be using some kind of electronic switching mechanism. Is anybody doing electrical engineering next year? Alright, come back in a year and tell me how they do it. I want to know the best way to convert AC to DC.
You're gonna learn that in first year.
You might, yeah, if you do electrical engineering. Okay, just before we finish, you can see that the field questions are sometimes good, sometimes bad. I just want to show you a recent one before you go. So this is 2015. Come on. Right. So this one here I just opened up on. This is nice. This is electric field lines around a point charge. That's actually an easy one. It's positive, so is it going in or do you draw it going out, in or out? Going out. And the equipotential, the circles, yeah. Determine the electrical force on a molecule with 3 excess electrons when it's midway between a 5 and a -3. Okay, so just maybe to draw this, here is 5 coulombs. Is it 5 coulombs? 5 microcoulombs. And here is -3 microcoulombs. And we want to know what is the force when you have 3 electrons in the middle. So you have a 3e here, and this distance is 10 centimeters, and this distance is 10 centimeters. Well, that's easy. What formula do you need here? How do you get the force here? No. Oh, come on, guys. This is exactly what I mean by the field question. Ah, this is section A, so you would have to do it. Coulomb's law. That's the one. So is this pushed left or right? Which way is the force here? Well, that's a negative and that's a positive, so it's left. And here? Left as well. So in this question, the total force would be K Q1 Q2 over R squared plus K Q2 Q3. over r squared. And what's nice is the r is the same for both. So actually you could just, you could just write it like this. And keep these all positive and say it's to the left as the answer. Yeah? I just want to leave you with one small question to try. It's related to this one. It's actually, I'm going to give you the same information. 5 microcoulombs, what was this, -3? Microcoulombs, and you have 3 electrons, and these are 20 centimeters apart. And I want to know, where do you put the electron? Is that going to be it? Positive, push it away, negative, pulls it. Yeah, I want to know, is there some place you can put these electrons so that the forces are balanced and it doesn't move? Because right now in this picture, which way will it move? Left. I want to know, is there somewhere you can put this electron so that the force is balanced? Yeah, well, what would happen if you put it here? It would be pushed to the left by the positive and pulled to the right by the negative. No? Sorry, positive. Oh, sorry, this is a negative. This is the positive pulls it to the right and the negative pushes it away. If you put it here, the negative will push it away, but the positive will pull it. So perhaps there is some place you can put it on the outside so that the pull and the push cancel, keep it balanced. I just want you to try this as a small homework, which we'll do in the next class, okay? Because this question came up, and the last time it came up, I think most people made a mess of it.
We didn't finish the position of 3.
Yeah. Now I don't know. I have a feeling that it'd be wrong to say it could be on either side. That it might turn out that there's only one position on one of the sides that work. Because these aren't equal, the picture isn't balanced. I suspect that only one of the sides would work. Yeah, but that one was a little bit easier because in both cases between the Earth and the Moon, it was a pull from either side, and the balance point will be somewhere in between. For this, interestingly, the balance point is somewhere outside the 2 charges, which makes it actually mathematically a tiny bit harder to solve than the example with the Moon and the Earth. Can you try this for me as a homework and see how you do? And we'll do this in the next class, okay? Alright.